Today we're going to learn about Euler's number, the number E. So a long time ago, some crusty old math dude by the name of Leonhard Euler, I'm sure he was crusty, maybe he was like the life of the party, I don't know, but he decided to take this expression 1 plus 1 over n raised to the nth and just start plugging in bigger and bigger numbers into n just to see what would happen. And so he did this a couple times, like 10 squared is 100, so he would do like 1 plus 1 over 100 raised to the 100th. He would do 1 plus 1 over 10,000 raised to the 10,000th, and so on. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And he noticed that as he used larger numbers of n, see how here we've got 2.7, then we've got 2.718, and then here we've got 2.718. He started noticing that this was approaching this number 2.78128, and then it kind of starts, the pattern starts repeating. This is Euler's number, and it is used with the natural log, which we're going to learn all about in the next few weeks. It is a very helpful number in math. It's kind of like pi. What is pi approximately equal to? 3.14. Euler's number, the natural base E, is approximately equal to 2.718. So just like pi, it has a button on the calculator that is the exact Euler's number, or natural base, but we can think of it as approximately 2.718. Now, before we get into using it in our calculator, let's simplify some expressions involving the natural base. Oh my goodness. There we go. So e to the third times e to the sixth. If you remember your properties of exponents, when we see multiplication, what are we going to do with our exponents? Add them. So e to the third times e to the sixth, add the 3 and the 6, that would give us e to the 9th. On the next one, I see division. When we see division, we are going to subtract our exponents. First, we need to think about 10 over 2. What is 10 divided by 2? 5. 5e to the second, because the e on the bottom basically has a little exponent of 1, and 3 minus 1 is 2. In number 3, when we see parentheses, we are going to multiply our exponents. So the 3 gets an exponent of 2, and then e to the negative 4x, we have to multiply negative 4x times 2 to get negative 8x. Can we have negative exponents? No. So e to the 8x goes to the bottom, and 3 squared is 9. 4, 5, and 6 are very similar, so try those on your own. On number 4, 2 to the third is 8, and e to the negative 15x, we need to put e to the 15x on the bottom. So 8 over e to the 15x. Number 5, we add those exponents. 2 plus 4 is 6, and 6 plus a negative 3 is 3. And number 6, we start by simplifying the fraction 8 over 6, that's 4/3. And then we subtract the 2x and the 3. But can you actually subtract 2x and 3? No. So you have 4e to the 2x minus 3 over 3, and that's it. That's all you can do. What if we have e squared times e to the 4x times e to the negative 6? You'd add those all together, but which two can you actually add together? The 2 and the negative 6? So we would have e to the 4x minus 4. You can't actually combine all those together, so you just leave them together in the exponent. All right, just like pi, e has a button on the calculator. So if you grab your calculator, whichever calculator you are most comfortable with, oh my goodness, e is the natural base. It is very related to the natural log. which on your calculator is ln. So to find E, you first need to find the ln button. On this graphing calculator, it's the third button up on the left side. If you have the typical TI-30X2S scientific calculator, it is the third button down on the left side. If you can find your LOG button, your LN button is probably right beside it. So on the graphing calculator, to use E, you push second and then your LN button. Most calculators give you this place to put in an exponent. So punch in 2 for your E squared and hit enter. You should get 7.389 as your answer, approximately. So when you plug in e to the negative 0.06, you should get 0.942. If you are getting numbers other than these when you try these on your calculator, please let me know so I can help you figure out how to do e on your calculator. When we graph, we are going to use the x values, -1, 0, 1, and 2. This is still exponential growth and decay. So in our x's, we're going to use -1, 0, 1, and 2. Now there's two ways that you can do this. You can grab your calculator and do 2 times e raised to the 0.75 times -1, and then write that number down as your y value. Then re-enter it, or do second enter to put it back in your calculator, and change the -1 to a 0, and write that number down in your table. So you can plug this in 4 times to get all of these numbers in your table. Or, if you're using a graphing calculator, you can use the shortcut. Do you want the shortcut? The shortcut is go to the y equals button and punch this equation into the y equals. So y equals 2 times e raised to the 0.75x. I honestly don't care about the graph right now. I really care about the table of values. So once you have that equation entered, push second graph. That will take you to the table. And basically you want this portion of the graph. You want from -1 x value to +2 x value. So copy these coordinates onto your paper. So for -1 we have 0.94. For 0 we have 2. 1 we have 4.2. And for the x value of 2 we have 8.96. It does not matter how you round these, because whether you graph 8.9 or 8.96, are you really going to be able to tell the difference on this graph? Probably not. Okay, so plot these points. And if you want to see what this graph looks like, you can push graph. It still has an asymptote, just like the other exponential growth and decay that we've been looking at. Okay, easy part. What's the domain? All real numbers. This is exponential growth and decay. So you still have all real numbers, just like before. The asymptote has not moved. The asymptote is at y equals 0. So what is the range? Y is greater than 0. Okay, now I need everybody to pay really, really close attention to number 12, because almost not almost everybody. A lot of people make a really silly mistake on number 12 and get it wrong on the test. And I don't want that to happen. So on number 12, if you type this whole thing into the graphing calculator, it'll be very difficult to tell which points you should actually pick for your table and which points you should graph. So you are going to take everything up to the x and stop. Notice number 11, there was nothing after the x. So we stopped after the x, there just wasn't anything after it. Anything that happens after the x is going to tell you how to move those points. So the +1 is going to tell us to move all of the points left 1. The -3 is going to tell us to move all of the points down 3. So the yellow part, that's the part that we want to put into the graph. So let me move this over. So y equals e raised to the -2x. Go into your table. And you want x values -1 down to 2. So -1, 7.4. Zero, 1, 1.1, and 2.02. Remember that these are temporary points. Each of these points will need to be moved. So when I plot this, -1, 7.4. If you'd prefer, instead of like making a little x, if you'd prefer to count to here and then immediately go left 1 and down 3 and put the actual point, that would be fine. 0, 1, 0.1. Each of these points I'm going to move left 1 and down 3. If we moved the graph down 3, what happens to the asymptote? It goes with it down 3, so our asymptote will be at y equals -3. So when we draw this graph in, this curves around very, very sharply. Okay, easy part, domain. How about the range? Y is greater than -3. The graph is above the asymptote, so it's y is greater than. The asymptote moved down 3, so y is greater than -3.